Thank you very much, and thank you also to the organizers for giving me the opportunity to speak in this very nice conference. So the topic of my talk is the failure of the curvature dimension condition in sub-Finsler manifolds, and you can basically think this talk as a part 2 of Giorgio's talk, which we try to prove the same result, extend the same result to the sub-Finsler setting. And essentially, as the name suggests, the sub-Finsler manifolds are the Finsler generalization of sub-Riemannian manifolds. And if you've worked a little bit in Finsler time spaces, you know that when you don't have a scalar product, but you have a norm, things can become very, very messy, very, very easily. And this is also because this is the reason why I will still go back to the introduction of the main concept that Giorgio already did, but in a more geometric way, because when you lose the infinitesimal Hilbertian structure, you also lose a lot of analytic properties, so I will be more focused on geometry instead of analysis. Okay, so first of all, the curvature dimension condition. I think you are all more or less familiar with this notion. It's formulated in metric measure spaces, and it's essentially asking a Kn convexity of Rényi entropies along Wasserstein geodesics. And this is a synthetic lower Ricci bound, and the reason why this is a nice synthetic lower Ricci bound is because of this theorem, which is a smooth theorem. So in the smooth setting of weighted Riemannian manifolds, this resulting metric measure space, where you put also a potential here, is a CDKN space if and only if the following Ricci lower bound holds. So this is the generalized Ricci tensor, and this shows that in some sense, in the smooth setting, this CD condition is coherent with this Ricci bound, and for this reason, it's a suitable synthetic Ricci lower bound. Okay, so what about sub-Riemannian manifolds? This is the same slide that Giorgio had, more or less, with the same definition, but before repeating in some sense the definition, I would like to give you an heuristic explanation of what's going on in these manifolds. So usually in the classical setting of Riemannian manifolds, when you want to define a distance, you take 2 points, and then you take all the curves joining these 2 points. You evaluate the lengths of these curves, and you minimize among all the length of this curve, and you end up with a number which is the distance between the 2 points. And in sub-Riemannian manifolds, you essentially want to do the same thing, but before starting this all minimization procedure, you fix at each point in the tangent space, you fix a subspace of the tangent, which will represent the set of admissible directions. And when you consider curves now, you want always to follow these admissible directions at every point. So you will not consider all the curves joining every 2 points, but you will just consider curves following specific direction that are a priori selected. And then you run the same minimization procedure, and you end up with the sub-Riemannian distance. And this is exactly the content of this slide. Of course, in the slide, it's made mathematically rigorous in some sense. So the proper definition is the following. So you take a smooth and connected n-dimensional manifold, and now a sub-Riemannian structure is defined by a generating family of vector fields, like this one. And keep in mind that so this number L and the dimension n are not related a priori. And with this generating family, you induce a distribution. At every point, the distribution is defined in this way. And it is a subset of the tangent space, and it aims at representing the set of admissible directions, right? On the distribution, we will ask this very important assumption, which is the bracket generating condition that also Giorgio, of course, was mentioning. And this essentially asks that taking Lie brackets of the smooth vector fields inside the distribution, you obtain after a finite number of Lie brackets the whole tangent space at every point. And we also have this rank function of the distribution, which is simply this function right here. So the rank in a point is none other than the dimension of the distribution at that point. Of course, being the distribution a subspace of the tangent, now this dimension will always be less than or equal than the dimension of the manifold. But in order to have a truly sub-Riemannian structure, we will ask this rank to be strictly less than n in at least 1 point, because otherwise, in every point, all the directions are admissible, and then we will end up with a Riemannian structure, which is, of course, interesting, but not interesting from this perspective. So with the generating family, you can also induce a norm defined on the distribution in this way. So I'm not really interested in this formula specifically, but I'm just interested in remarking that in this way you can induce a scalar product at every point, which is now defined only on the distribution, so not on the whole tangent space. So this is also the reason why you just consider admissible curves, meaning curves having velocity inside the distribution at every point. And the reason is that you can evaluate the speed of curves only if their velocity is lying in the distribution. And then if you take any admissible curve, you can define the length in this very natural way using the norm on the distribution. And then you can run the same length minimization procedure that I was mentioning before, and you will end up with the sub-Riemannian distance. And the bracket generating condition, this one, it's fundamental because it ensures that the distance to be finite, continuous, and to induce the same topology of the manifold. Okay, so these are the same two examples that Giorgio presented, but I would like to point out some geometric properties of these two examples. The first one is the Heisenberg group. In this case, the underlying manifold is R3, and the generating family is composed by these two vector fields. So we have topological dimension 3, but two vector fields, so we have rank 2. So in general, at every point, not all the directions will be admissible. In particular, if we are in the origin, like here, the admissible directions are the horizontal ones, as you can see from this expression. So in particular, if we want to join the origin with a point on the same vertical, as in this case, we cannot go straight up. We should move a little bit in order to fill these other contributions in the vertical direction, and then we can start spiraling up and reach a point on the same vertical. And this is exactly what happens, and indeed, the geodesics are spirals like this one. Another example, which is very much related but completely different, is the Grushin plane. And in this case, our manifold is R2, and the generating family is this one. So we have dimension 2 and two vector fields, but one of the two is vanishing on the singular region x equals 0, as it represented here. And so, in general, outside the singular region, we'll have dimension 2 and two vector fields. So all the direction will be admissible. In particular, locally, outside the singular region, we will look like a Riemannian manifold. But when approaching the singular region, we will see the singularity and we will see the vanishing of this vector field. In particular, you can see in the figure, represented with this gray set is the ball of radius 1 centered in the origin of the Grushin plane. And you can see that in the direction, in the y direction, we can feel really the singularity induced by the structure. But of course, these two structures are very different, and this motivates the following definition. So we say that a sub-Riemannian manifold is almost Riemannian if the rank of the distribution is equal to the dimension of the manifold at almost every point. So of course, with this definition, the Grushin plane is an almost Riemannian manifold, while the Heisenberg group is not. And in some sense, almost Riemannian manifold can be considered as like non-complete Riemannian manifold, and as metric measure spaces, they are very close to Riemannian manifold, much closer than a sub-Riemannian manifold like the Heisenberg group, for example. So what about the CD condition? Giorgio already told us about it. And in sub-Riemannian manifold, the CD condition cannot hold. This is the precise statement saying that a complete sub-Riemannian manifold equipped with the positive smooth measure and, of course, with the sub-Riemannian distance cannot satisfy the CDKN condition for any choice of the parameters k and n. So this is not about optimal constant. This is really showing that the CD condition fails to describe curvature in a proper way in these spaces in particular, in contrast to what happens, of course, in Riemannian manifolds. And as Giorgio was mentioning, this result was proved through successive contribution. Here I just put 3 of them, which in my opinion represent the 3 main possible strategy to prove this theorem. So the first one was proposed by Julien, and he proved the statement for manifolds having rank strictly less than the dimension at every point, so like the Heisenberg group, for example. And his strategy was to construct 2 suitable sets to contradict the Broom-Minkowski inequality, which is a consequence of the CD condition. The second strategy was proposed by myself and Tommaso Rossi 2 years ago. And with this strategy, we were able to prove the result for almost Riemannian manifolds. under this additional assumption, which is rather technical and I don't want to comment about. And our strategy was to contradict the one-dimensional characterization of the CDKN condition, which was proposed by Cavalletti, Mondino, Millman, and maybe other collaborators that I'm forgetting. And both these two proofs are essentially geometric. So they use the smooth structure of the space, but essentially they are geometric proofs that consist in some geometric construction which are related to the CD condition, but they have really a geometric flavor. Where the last one, which in some sense is the best one because it allowed to prove the general statement, it's an analytic proof, as Giorgio was telling us. And so for the proof in the general case, they contradicted the validity of the sub-Riemannian Bochner inequality. So their proof was, okay, in the end was also geometric, but it started as an analytic proof relating the sub-Riemannian Bochner inequality to the curvature dimension condition. Okay, so what about sub-Finsler manifolds then? So the main topic of this talk. So first of all, what are sub-Finsler manifolds? It's pretty intuitive. Probably you can already guess what they are, but properly in a mathematical proper way, sub-Finsler structure on a smooth manifold is defined by a generating family of vector fields as before, but now we also consider a norm which is on RL, where L is the number of these generating vector fields. And as before, we have a distribution. We ask the bracket generating condition, which once again, of course, is fundamental. And as before, we induce a norm on the distribution, but now when we are defining the norm, we also take into account the reference norm. So here, in this part here, we actually have this reference norm. And in the sub-Riemannian definition here, you essentially have the Euclidean norm, while in this case, you have a general norm. And for this reason, you don't end up with a scalar product defined on the distribution, but you end up with any possible norm on the distribution. And this is, of course, the measure difference. So for the usual length minimization procedure, everything works as before. The distance is quite nice, and but it's continuous and induces the same topology. But in general, if the norm is bad, the structure is bad. This is the takeaway from these three pictures that now I'm going to explain. So first of all, these two pictures essentially are representing the Heisenberg group with reference norm L infinity. So in the Heisenberg group, we have two vector fields, and we should take a norm on R2, and we can, of course, take the L infinity norm, this one, so the maximum between the coordinates. And so in the Heisenberg group, the geodesics are still spirals in some sense, but are weird spirals, like this one, a union of segments. So not a nice circular spiral as before, but non-smooth curves like this one. And you can deduce from this picture that the distance is also singular. In fact, this is the sphere of radius 1 centered in the origin, and you can understand from these flat parts that the distance is not smooth in this case. So the takeaway is that if the norm is not regular, if the norm is not nice as this one, then also the structure is much more complicated and singular. So before going on, I would like to go back, because now we want to prove the same result for sub-Finsler manifolds, so it's natural to ask if one of these strategies can work in the sub-Finsler case. So of course one should try this before, because it's the most efficient one, but being this a really analytic strategy, it's very difficult to use it in sub-Finsler setting, especially if you allow any type of norm on the distribution. And this is why, and also like this intermediate strategy here is geometric, but still uses a lot the smooth structure. And also we are not really interested in this case for reasons that will maybe be clear at the end of the presentation, but we are more interested in this case here. So it's quite natural to start to generalize the strategy of Juliet also to the context of sub-Finsler manifold. And this is exactly what we did together with Tommaso Rossi last year. We were able to prove essentially an analogous of Juliet result in the sub-Finsler setting, which is exactly this one. So as Juliet, we assume this inequality, strict inequality on the rank function at every point, but we also needed to assume some properties of the norm on the reference norm. So we assumed the reference norm to be smooth and strongly convex. Of course, this is a relevant assumption. It's not. And under this assumption, though, we were able to disprove the CD condition. So we had the same result as in the sub-Riemannian case. So this result is very general in terms of structures. Indeed, we only have this assumption on the rank, which is not that strong, I'd say. But it's not very general in terms of norm, because indeed we have to consider smooth norms, which are also strongly convex. And according to last slide, of course, the more the norm is singular, the more the structure is bad. So in some sense, these are the nice sub-Finsler manifolds. But we also have a second result, actually, which is not very general in terms of the structure, because it's just for the Heisenberg group, but it's completely general in terms of norms. In particular, given the Heisenberg group equipped with any norm and with a positive smooth measure, then the associated metric measure space cannot satisfy the CDKN condition. And in some sense, the combination of these two results motivates the following conjecture that I'm going to read and then comment. So the conjecture says that for any truly sub-Finsler Carnot group equipped with any norm and with a positive smooth measure, we claim that the resulting metric measure space doesn't satisfy the CDKN condition. So same result. So you may wonder, what are these sub-Finsler Carnot group? In some sense, you can think those as sub-Finsler manifold that also have a Lie group structure. So in some sense, they are nice sub-Finsler manifolds. And why is this conjecture motivated by these two results? So first of all, the Heisenberg group is the easiest example of Carnot group. So in that case, we really have validity of this conjecture. While, moreover, Carnot groups always satisfy this rank assumption. So in some sense, this is saying that if the norm is nice on the Carnot group, then the conjecture holds. And the importance of this conjecture and why we're interested in this conjecture would be clear at the last slide. So you have to be patient. Yeah. Yes. The second one, yes. But the measure has to be positive, though. Positive and smooth. Okay. So I will not speak about this one because actually the proof is rather technical, and the strategy is similar to Juliet's one, but it's much more complicated to run it. But in this talk, I would really make you understand how it's possible to treat all the singularities that arise from singular norms. And so I will focus on this second result. And the reason why we're able to do so in the Heisenberg group is that in the Heisenberg group, we are actually able to have an explicit expression for geodesics. And this explicit expression is given in terms of convex trigonometry that now I'm going to speak about. So first of all, we have a reference norm on R2 in our Heisenberg group, and we consider the unit ball of this norm, and we call pi omega. So omega will be this unit ball, and pi omega will be its area. Okay, and now on this domain right here, which is the generalized domain, we can define trigonometric function as explained by this figure. So given theta in this domain, we take p theta as the point on the boundary of omega, such that this area inside here is omega over 2. Sorry, theta over 2. And then we project this point, and so the x projection will be the cosine omega of theta, and the y projection will be the sine omega of theta. So in this way, on this domain, we are able to define trigonometric function. Of course, if you take the Euclidean ball, you end up with the usual trigonometric functions, but in some sense, these are trigonometric functions that also take into account the geometry induced by the norm. Okay, so you can also take the dual norm, for example, of our generating norm, and you can call omega 0 the ball of the dual norm, and call, as before, pi omega 0 its area. And of course, once again, you can run the same procedure and define trigonometric functions like this one, sine omega 0 and cosine omega 0, of course. And now we can define the correspondence between angles in these two domains. So we take theta in this domain, in the primal domain, and phi in the dual domain, and we say that these two angles correspond to each other if this scalar product is equal to 1. So in general, these points are on the boundary of the unit ball, the primal unit ball, and the dual unit ball. So for general angles, we will always have the less than or equal. And we're simply saying that the angles correspond to each other if the scalar product is, if we have equality, essentially. And in this sense, since there is a duality going on, the correspondence really represents the duality, but at the level of generalized angles instead of vectors, essentially. So two angles are in correspondence if their associated vectors are one the dual of the other. And according to this relation, we can actually define also the correspondence map, which I remarked that starts from the dual domain and goes to the primal domain. And it's defined in this very simple way. So to each angle, we associate all the angles that correspond to our argument. And this correspondence map is actually a central object of our analysis. And this is due to two main reasons. The first one is that this correspondence map naturally appears when you want to take derivatives of trigonometric functions. So if you want to take the derivative of sine omega 0, you end up with cosine omega, and there's a nice duality, but this is evaluated now in the correspondence of our angle phi. And the same, of course, for the cosine omega 0. And the second reason why this is so important is that the properties of C0 actually depend on the regularity and on the convexity of the reference norm. Okay, so this was it about trigonometric functions. And so now we actually have geodesics in this case, and those geodesics are written in terms of these trigonometric functions. So this is, in some sense, an exponential map. So t is the time parameter, and this is the other spatial parameter in some sense. And this is the expression of the geodesic. It's very complicated, but I will comment about it in a second. So these are actually geodesic because this is actually what holds in this case. And for every parameter like this curve is a geodesic up to a cut time, which is this one. And okay, so first of all, what is this telling? In the case omega is equal to 0, it's essentially telling that horizontal half lines starting from the origin are geodesics in this case, so this is quite nice. And what about the case omega different from 0? This is the expression of the geodesics. So the z coordinate, it's quite complicated. I don't want to think about it. So just focus on x and y. So when you're like making t vary from 0 to 1, let's say, so this quantity is fixed, and also the prefactor is fixed. So essentially, what you will see is like this x and y will vary as trigonometric functions. So essentially, if you project the geodesic on the horizontal plane, you will see the profile of the ball, because this is exactly what is described by trigonometric function if you think those like as two variables combined. And so this is what happens in the sub-Riemannian Heisenberg group. As you can see, the projection now is the boundary of the ball, the Euclidean ball, so it's a circle. While for example, in the L infinity Heisenberg group now, you still have a spiral, but now the projection is not a circle, but it is the square, which is the ball, so the boundary of the ball of radius 1 of our norm. Okay, so once we have this like sort of exponential map, we can also evaluate the Jacobian. So now this is super complicated. I don't want you really to understand this because it's probably not worth it. But I just want to point out that in this Jacobian now, this correspondence map is appearing. And the reason is pretty simple because of what I told you before. I told you that when we are trying to derive trigonometric function, the correspondence map is appearing. And of course, as the exponential map was given in terms of trigonometric function, when we are deriving it, of course, the corresponding map will appear. So it's pretty natural to have a corresponding map inside the Jacobian. And in this expression, like every function is essentially nice except from this correspondence map. And so what we can observe is that the regularity of the Jacobian, and therefore the regularity of this exponential map, depends on the regularity of the map C0, because every other function is essentially nice. And as the regularity of the map C0 is related to the properties of the norm, we can conclude that the regularity of the Jacobian and therefore of the exponential map depends on the properties of the norm. And this is something that we can actually exploit to prove our main result. And the reason the Jacobian is very important is due to the measure contraction property. I will not go through the definition, but you probably know it. You can interpret the measure contraction property as the generation of the CD condition when one of the two measures is converging to a delta. And so this is the definition, but the main things why the measure contraction property is useful for us are these two. So the first one is that it's weaker than the CD condition. And remember that we are trying to contradict the CD condition, so if we are able to show the failure of MCP, automatically we will show the failure of the CD condition. And the second one is that MCP can actually be characterized in terms of the Jacobian, and this is something that we proved. And in particular, having the Heisenberg group with any norm and with the Lebesgue measure, we are able to prove that MCP is 0n holds if and only if we have this inequality between the Jacobians for every parameters and every time. Okay, and this is actually something that we can exploit to end up with this theorem. So this is a slide full of theorems, but let me start one step at a time. So the first theorem is actually telling us that when the norm is not nice, when the norm is bad, MCP cannot hold. So if we have a norm which is not C1 or not strongly convex, then the associated Heisenberg group equipped with a positive measure doesn't satisfy MCP for any choice of the constants. However, if the norm is quite nice, in this case C11 and strongly convex, the Heisenberg group with the Lebesgue measure satisfies the measure contraction property 0n. Okay? However, when the norm is nice, we are able to contradict the CD condition. So when the norm is C1 and strongly convex, the associated Heisenberg group cannot satisfy the CD condition. So a brief recap. If the norm is bad, MCP fails, and therefore CD fails. And this is when it's not C1 or not strongly convex. If it's both C1 and strongly convex, we are still able to disprove CD. And so we have a general result about the CD condition. And in some sense, this theorem too shows that we really needed to contradict CD and not MCP in this regular case, because when the norm is nice, MCP actually holds. So we really need to contradict CD, which in principle is much more difficult with respect to contradict MCP. So once again, I will focus to the case of singular norms in order to make you understand what's going on. And yeah, so this theorem actually has two separate cases. So the one when the norm is not C1 and the other when the norm is not strictly convex. And actually we have two different strategies in this case. So when the norm is not regular, so not C1, we're able to find a set of parameters, A, such that the Jacobian is 0 for every time sufficiently small for every parameter in this set. And essentially what happens is that we have branching of geodesics. So starting from the origin, for example, we have geodesics behave like this. So they start, we can find a set of parameters such that all the geodesics in this set of parameters are in the same direction, and then at some point they start branching out. And this is a pretty peculiar behavior, because actually we have branching of geodesics, but we have uniqueness, at least local uniqueness of geodesics. So geodesics branch, but they are unique. And this is quite uncommon because usually when, in the easiest example, when we have branching, we also have non-uniqueness. But this happens when the norm is not regular. And of course, in this case, MCP cannot hold because you're shrinking too much for small times. You know about MCP, but this is actually, and you can also think about this in terms of our characterization, because if the Jacobian is 0, we go back a little bit, for small times, then this cannot be greater than or equal than something, which in principle is positive. If instead the norm is not strongly convex, the Jacobian, as a map in this way, fails to be Lipschitz. So we can exploit this to find a specific parameter and specific times for which this inequality, this characterization that we had, can actually be contradicted. And this shows that essentially the relation between the properties of the norm and the Jacobian is actually very useful for us, the relation that we evaluated explicitly calculating the Jacobian. So this was about the negative result. How much time do I have? 15 minutes, okay. Okay, so I also can talk about a little bit about the positive result, which is this one. This is exactly what was in the previous slide. So this is the result that we have. So when the norm is nice, meaning C1 and strongly convex, and equipped with the Lebesgue measure, then the resulting metric measure space satisfies the measure contraction property for some n. So in principle, this result is for some constant and not with a specific constant. But actually, this is a work in progress, but I think we are essentially done with this, the hard work, and we just have to write it. We were able to have an estimate, to prove an estimate on the so-called curvature exponent. So essentially, in a space, in a metric measure space, general metric measure space, in which the MCP 0n condition holds, we can define the curvature exponent as the optimal constant for which MCP holds. And in this case, as the MCP condition is monotone with respect to the constant n, this is the infimum of all the n's for which the MCP condition is satisfied. So this is called the curvature exponent, and it's well known now that the curvature exponent in the sub-Finsler Heisenberg group is equal to 5. So essentially, the dimension of MCP is equal to 5. And what we are able to prove now with the same authors is that given any sub-Finsler Heisenberg group equipped with any norm and with the Lebesgue measure, then the curvature exponent is bigger than or equal than 5, and equality holds if and only if the norm is induced by a scalar product. So in the end, if you are a sub-Riemannian Heisenberg group. And this is quite interesting because it's saying that for MCP, the best case is when you actually have the Riemannian norm. And this is not, if you think about the situation in Rn with norms, this is not something you really expect. But in this case, we were able to prove this result. And yeah, so in some sense, the sub-Riemannian Heisenberg group is optimal for this. Okay, so this is in some sense a recap slide. So, table that's probably like explaining what is going on. So first of all, for bad norms, we have that MCP fails. And as a consequence, as MCP is weaker, we have that CD fails. Then for all the other cases, so which is the union of these two columns, so for C1 and strongly convex, we have a completely different strategy to prove that CD is failing as well. So not as well. So CD in this case is failing, and actually the proof in this case follows in some sense the lines of Julier's proof once again. But of course, it needs to be really adapted to this highly non-regular setting. But in this case, so when the norm is particularly nice, even if C1 and strongly convex is not particularly strong as an assumption, but we are able to prove MCP for some constants. And in particular, we also have a bound on the curvature exponent. And in some sense, we are left in this very weird intermediate case in which we have a norm which is C1, but not C11, and also strongly convex. And unfortunately, in this intermediate case, we were able to highlight different behaviors. In particular, this is a theorem that we proved that is indeed a sufficient condition to satisfy MCP for some constants, but we were also able to prove with a counterexample that this is not necessary. And we also guessed some different possibilities of necessary and sufficient conditions for MCP to hold, but all of them were in some sense ruled out by examples or counterexamples. So this case seems pretty much impossible to treat, like in an easy way at least. Okay, so finally, the motivation of this whole work in some sense, and the motivation why we're so interested in studying the CD condition in sub-Finsler kernel groups. And the motivation is that essentially these spaces, these sub-Finsler kernel groups, are naturally arising as metric measure tangents of metric measure spaces when this metric measure tangent is unique. And this is exactly what is explained more or less in this slide, but we will come to it. First of all, let me recall the conjecture, which was this one. So for any truly sub-Finsler kernel group equipped with any norm and a positive smooth measure, we claim at least that this space cannot satisfy the CDKN condition. Okay, so now let's take a generic CDKN space. And for a CDKN space, we can take tangents. So how can one define tangent in a point? It's simply the limit with the pointed measure ground-Wavdor convergence of this type of rescalings. So essentially, even if you don't really know the definition of it, you fix a point and then you zoom in around the point and you take the limit with respect to the measure ground-Wavdor convergence. In principle, you will have more than one tangent, but any limit of this procedure will be considered a metric measure tangent for, of course, a sequence of zooms that are going to zero. So this is a metric measure tangent. And suppose for a moment, so in general, this slide is not supposed to be a proof. It's just a sketch of a possible strategy in which we could use this conjecture. So suppose for a moment that at almost every point, there exists a unique tangent up to isometry. This is, of course, a very, very strong assumption, but let's say for a moment it's true. So then if this tangent is unique, so first of all, it is a tangent of a CD0n space. Therefore, it is a measure Gromov-Hausdorff limit of a CD0n space, of a CDKN space. And therefore, due to the scaling property of the CD condition and the stability property, we can deduce that the limit is itself a CD space, in this case, a CD0n space. Then, we also know, due to this result by Enrico Ledonne, that the tangent, metrically, is a sub-Finsler kernel group. And this is a very nice result, telling us that if the metric tangent is unique, then it is a sub-Finsler kernel group. So in this case, we would end up with a metric measure space, which is CD, but also a sub-Finsler kernel group. And according to our conjecture, this is not possible. And so this will imply that, in some sense, the tangent is a degenerate kernel groups, meaning it is a Banach space. In particular, Banach space are kernel groups in which the rank of the distribution is equal to the dimension. And of course, they are degenerate kernel groups because they have the usual Banach geometry. So in this way, we will be able to prove that the tangent is a Banach space at almost every point. And actually, this result will be enough to conclude rectifiability according to a very recent and nice result by David Bates. And I've included this slide because I think it's a strong motivation, and also because it's quite remarkable for me that with a strategy like this, we can, so usually you start from a particular result, and then, so what I want to say is essentially that in this way we would like use result in this specific setting of sub-Finsler manifold to prove a very general result for non-smooth spaces. And this is in some sense quite remarkable, and it's essentially due to this result by Enrico Ledonne, and this is essentially our motivation to go on and try to prove this conjecture. So this is the last thing I wanted to tell you, but before opening the discussion, I would give the word to Masha for a second. I don't know.